Hello everyone, welcome to our presentation. The title of our work is Anisotropic, Separable, Set Abstraction for Efficient Point Cloud Representation Learning. My name is Guocheng Qian. This is a collaborative work with Hassan Hamad, Guohao Li, Ali Thibat, Bernard Galim. We are from King Abdullah University of Science and Technology. The motivation behind our work is new mobile devices, embedded LiDAR sensors have created a need for efficient point cloud learning algorithms. We have seen such LiDAR sensors on iPhone and on many VR equipment. We'll see more and more such LiDAR sensors in the mobile devices. However, current state-of-the-art point cloud algorithms increase their accuracy at the expense of the speed. For example, the recent algorithm KPConv and Postpro, they achieve impressive results on SADS segmentation. SADS is the largest scalar point cloud segmentation benchmark. They achieve mean MOU over 60. However, their speed is 200 less efficient as PointNet. On the other hand, PointNet is fast, but it's not that accurate. The mean IOU on SADS area 5 is lower than 45%. In this paper, we focus on processing some architecture that can achieve good balance between accuracy and speed. At first, we revisit PointNet++ for its wide applications and its good accuracy and speed balance. PointNet++ has been used everywhere, like normal estimation, point cloud segmentation, and object detection. Our question is, can we make PointNet++ faster and more accurate, such that it will be beneficial for those downstream tasks? For the background information, we present PointNet++ architecture and the set abstraction module. Set abstraction, SA, module is the basic building block of the PointNet++. SA module consists of three parts: subsampling, which is to downsample the point cloud to a smaller set; grouping, which is to query the neighborhood points for each point inside the point cloud; and local aggregation, which is to aggregate the local information from the point neighborhood. The aggregation part is usually done by several layers of MLPs, followed by a reduction layer. The reduction layer is mostly an average pooling layer or max pooling layer. We conduct latency analysis on PointNet++. We show the inference runtime decomposition of PointNet++ and a different number of points as input on one GTX 2080 Ti GPU. The latency of PointNet++ can be decomposed into three contributing facts: subsampling, grouping, and computation. The computation will mainly mean the aggregation layer, the MLPs, and the reductions. We discovered that the actual computation is the latency bottleneck of the architecture. So, why is PointNet++ slow? PointNet++ is built by the Vanilla SA module. We named the SA module proposed in PointNet++ as Vanilla SA. The question is, why is Vanilla SA slow? We show the SA module at the red figure. We can see that MLPs is performed after the grouping layer. That means the PointNet++ performed MLPs on the neighborhood features. The neighborhood features is with size nck, which is k times bigger than the point features, which size is nc. So the straightforward remedy is, can we perform MLPs on the point features directly? This reduces flops of each MLP by a factor of k. K is the neighborhood size. Why is the Vanilla SA inaccurate? This is because all the MLPs and the reduction layer are unnecessarily isotropic. They treat all points and their labels equally, which extremely limits the representation capability of the network. Why? Because MLP is the shared MLP, and average pooling is the pooling that with the weight of all the labels equal to 1. In this work, we gradually modified the Vanilla SA module to improve its efficiency and to improve its accuracy. We at first proposed pre-conv SA module. As shown at the red figure, The difference between our pre-conf assay module with the vanilla assay module is we move the MLPs to before grouping instead of after grouping. This means our proposed pre-conf assay module performs MLPs on the point features directly instead of on the neighborhood features. Given a point features, we process its feature by a shared MLP. Then we query the neighborhood features, query the neighborhood for each point. Then we perform the reduction layer along the neighborhood dimension. The proposed pre-conf assay module reduces flops of each MLPs by a factor of k. We further propose separable assay module. Compared to the pre-conf assay module, our separable assay module separates the MLPs to before grouping and after reduction. And then we add the residual connection between the two parts of the MLPs. The separable assay module is inspired by the depth-wise separable convolutions in image domain. We introduced it to the point cloud domain and also separates convolutions to linear channel correlation using MLPs and learning the spatial correlation using the grouping and the reduction layer. Finally, we propose anisotropic separable set abstraction, ASSAnet module. The first two variants mainly focus on improve the efficiency of the vanilla assay module. This does not change the isotropic nature of the vanilla assay. So here, in our final version, we introduce the anisotropic operation into the assay module. We replace the reduction layer by our proposed anisotropic reduction layer, and therefore improve the accuracy. The anisotropic reduction is formulated in the following. Given a point features, we process that by a shared MLPs. We then query the neighborhood for each point. We scatter the neighborhood feature by the relative position of the neighborhood points to the center point. We concat the three scattered features together. We then perform a reduction layer along the neighborhood dimension to obtain the aggregated neighborhood information. We process the aggregate neighborhood information by a shared MLP again, and added that back to the point features using the shortcut connection. The ASSAnet module is shown at the right figure. It performs MLPs before the grouping, then query the neighborhood features, then do the anisotropic reduction, and followed by MLP layers. The two outputs of MLP layers are added together. We showed latency decomposition of the ASSAnet module and the ASSAnet module. We find that our ASSAnet module has a 4 times reduction in the latency. We replace the vanilla ASSAnet module in .NET++ with our proposed ASSAnet module. The modified architecture is referred to as ASSAnet. The proposed ASSAnet is much faster than both .NET++ and the state-of-the-art networks. We now consider scaling up the ASSAnet. We consider two methods to scale up our network. One is the wider scaling to increase the channel size, and another is depth scaling to increase the number of aggregation layers in one assay module. We named the large ASSA network with channel size 128 and the depth 3 as ASSAnet large. The experiment part. On S3DS segmentation, which is the largest scale of point cloud segmentation benchmark, we achieve amazing result. By simply replacing the vanilla assay module inside .NET++ with our proposed ASSAnet module, we can see a 7.4 mean IOU improvement. And also we have the 1.6 times faster speed. The large network can more accurate result and outperforms the previous state-of-the-art with much higher speed. We showed evaluation also on SADIS. Our proposed ASS module outperforms other format of the assay modules in both accuracy and speed. We showed that our network can be easily scaled by either increasing the widths or increase the depths. On MobileNet 40 classification and ShapeNet part segmentation, we also achieve better result and faster speed than PointNet++. For better understanding what happens in ASS module, we visualize the feature patterns learned in the first ASS module. We found that ASS module helps capture better geometric relationships. We used the airplane in the ModelNet 40 dataset as an example. We showed feature patterns of the before the first ASS module and after the first ASS module. We can find that after the ASS module, the feature length captures more relationships. For example, the head of the airplane, the wings of the airplane, and the tail of the airplane are captured in the same time. This is not happened in the patterns before ASS module. We find the same thing happens in the other classes. More visualization examples are available in the supplementary file. We dive deeper into PointNet++. We find that PointNet++ suffers from the computation burden attributed to the MLP's process on the neighborhood features. We discovered the accuracy of PointNet++ is limited by the isotropic nature of its operations. To reduce the computation and improve accuracy, we propose pre-conv assay module, separable assay module, and finally the anisotropic separable assay module. We replaced the vanilla assay module in PointNet++ with our ASS module. We name our architecture as ASSANet. Extensive experiment was conducted to verify that our module can largely improve the accuracy and achieves faster speed on various point cloud tasks. The scaled ASS module also set new state of art on various tasks with faster speed. The current state of art is accurate but slow. PointNet++ achieves good balance between accuracy and speed, but our ASSNet is faster and more accurate. Thank you for listening. The code is available at GitHub. Please try it out, and if you have any questions in regards to the paper or the code, please contact me through the email.